So yeah, today we'll just talk about homework 1. Yeah, since I'm basically or showing the solutions, I probably just will not bring up the homework as I'm going to post it online. So yeah, so I just so for the first question is asking about I think sum of 16 independent random variable. Each of them follow a normal with mean 0 and sigma square equal to 4. And the question is asking first regarding to the distribution of x bar, and then our quantity of interest is this absolute value of x bar less than or greater than c, that this happens, or this, the probability of that equal to 0.9, and find the value for c. So yeah, start from the given individual random variable x follow normal, and then we now develop the distribution for x bar. So x bar is just average of, or just the 1 over n multiplied by the summation of all 16 random variable. So that here I use the subscript to differentiate from the mean and the variance from the individual random variable x. So x bar has a mean that is also equal to the mean of the individual component. So x bar equal to mu, where mu is just 0. And then sigma square, the variance of the x bar is just the variance of the individual random variable divided by n, where n is the number of random variable. So 4 divided by 16, which gives 1 over 4. So this is the distribution for individual random variable, and this is the distribution for the x bar. And once we have that, which also follow a normal distribution, and then we can now evaluate this quantity here. So absolute value of x bar less or equal than c. We can expand that as between a range. So x bar fall between negative c and positive c. So x is a general normal distribution. We can apply some transformation to convert this x bar into a standard normal distribution by minus the mean of the x bar and then over the standard deviation of the x bar. So we apply the same procedure for all the components inside the parenthesis, and then we basically reduce a general normal to a standard normal distribution. So we have z fall between negative 2c and positive 2c. And then from here, we can use the CDF for a standard normal. And then, we will reduce to this expression. So the CDF of 2c is equal to 0.95, and then find the value for c. You can start from there to convert a quantile to convert a PDF to quantile, and then from quantile to solve for c. Any question or comments? Sorry, what?
Where did you get that like 3C and negative 3C from?
Which part? Do you mean this one? Which line?
The down line.
You mean this 2C and this one?
Yeah.
So from here we know that the mu of x bar is 0, and then the variance of x bar is 1 over 4. So you just plug in the number here. So negative c minus 0 over 1 half. And then it will become 2c and negative 2c. Yeah.
It's not function.
This one? Yeah, this is just a notation for standard normal. Is that what you're asking for, or?
Okay. So the input is the 2C, and the output is like what you get from like the z-score or like the z-table, or?
Are you familiar with p-norm in R? Basically, that is what. So, input is a quantile, and it returns a probability 0.95.
Okay.
Yeah. So yeah, that is basically the p-norm in R.
Okay.
Yeah. and that capital phi is referring to standard norm, the CDF of a standard normal. Any question or comments? Okay. Yeah. Yeah.
Is the question is asking for derivative phi inverse of 0.95?
Yes. So basically, yeah. So you just find a value c such that this quantile under the standard normal distribution will give you 0.95 probability. So you just reverse. Yeah. Mm-hmm. So yeah, given CDF, so given the quantile, you can find the probability, and then inverse is just given the probability, you can find the quantile. Yeah. Any other question or comments? Yeah. Sorry, what? Go. Yeah. Sure. So this is the distribution for individual component, individual random variable. We have 16 of them. And the question is asking for x bar, or some quantity of interest. But the baseline is that we need to know the distribution for x bar as well. So x bar is just the average of the 16 random variable. So now because individually they're also following normal. So by taking the average, and they also follow normal. But the mu of the x bar, in this case, is equal to mu. Basically, it's the we have n copies of mu, and then we divide it by n, so it becomes stay as mu as mu. But for the variance is we have n copy of sigma square, so n multiplied by sigma square. But when we divide it by n, when we plug into this variance, we have to divide it by 1 over n squared, so that we have a divided by n here. So this will be the mean and the variance for the x bar. And when plugging the number, we have 0 and 1 over 4. And once we have the distribution for x bar, we can now solve for the quantity for this one. So we expand that. It basically is the x bar fall in between these two in this range. And then this is x bar is a general normal distribution. So we apply transformation to reduce that to a standard normal distribution. Basically, it just ease our computation. And then from there, plug in the number, the 0 and 1 over 2, or the variance 1 over 4. And then we will get this part here. And then basically we just need to play around with the CDF of the standard normal. And we reduce to this expression. And we are asked that what is the value of C for this quantile that under the standard normal distribution will give us the probability of 0.95. Does that make sense? Good. Any other question or comments? Okay, then for question 2. So, yeah, so we are also interested in this quantity here, x bar, absolute value of x bar less than or equal to 0.1. And this events with probability 0.9. So we expand this term here, fall between this range, negative 0.1 and positive 0.1. We apply the same transformation, and then that will reduce to a standard normal. So this will be a z. And this time, yeah, we don't know the number of n. So here I just use n2 as a placeholder for now. So x bar also follow a normal distribution with mu of the x bar equal to mu, the mean of the individual random variable. And then the variance of x bar is also x sigma square over n. And so this is the distribution for x bar, but with an unknown for now. And now we can just plug in the number to mu of x bar and the standard deviation of x bar into this form with the n, well, implicitly or plug in as an expression here. And then we basically it's the same idea. It's instead of solving for c, now we solve for n. But the idea is very similar to question 1, except that we are solving for n for now. Any question or comments? Okay, then for question 3. So we have the expectation or the mean of random variable x is equal to 15 and the standard deviation of x equal to 10. And we are interested in the, I believe that question is asking the total weight of 100 package exceeding 1700. So we are interested, the random variable that we are interested is this, I denote it as S, which is the sum of 100 random variable X. Each of them has expectation and variance with these two quantity here. And because we can consider 100 as a relatively large number, so the summation of them can be approximately a normal distribution. So this time the mean of the random variable s, which is the sum for the 100 random variable, it's n multiplied by the mean of the individual random variable. So it's n multiplied by mu, which I use a subscript x for that. So yeah, it's always a good habit to write down the subscript just to differentiate which term you are talking about explicitly. So the mu of s is equal to n times the mu of x. And the variance of s is also n multiplied by variance of x. Yeah, and then we can just plug in the number, and then we will have s approximately following normal distribution with mean 1500 and the variance 10,000. And then the quantity of interest is the probability of s greater than 1700. But for now, I'll just calculate less than or equal to 1700. And then once we find the probability for that, we can just do 1 minus, and that will be the probability of exceeding 1700. So s is less than or equal to 1700, we can apply the same transformation. So minus the mean and over the standard deviation. So minus 1500 and then over 100. 100 is the standard deviation, that is the variance. And then we will have z less than 2. And then, yeah, so this time we are trying to find the probability for that. So yeah, in R you can call P norm here, and that will be your probability. And don't forget 1 minus if you are first solving for the lower tail. The question is asking for the upper, for the other side. Any, yeah.
So the reason why which is the sum from x to 100 is equal to n times us, like the mean and the standard deviation are both multiplied by n, is because you're adding all of them together, right?
Yes.
Whereas before you take the average, so you
Yeah.
don't have to multiply by x.
So if it is the average of them, then you still have to divide it by n, and then it becomes mu of x. As the previous question, mu x bar just equal to mu. But here we're talking about sum, so we did not divide it by n, so we keep the n over there. Yeah. But when divided by n in the variance, it should be divided by n squared. So that is why in the previous one we have a sigma squared over n. But since we did not divide it by n squared, so the n stay there. And another assumption that we are able to do that is that if you look at the question, we have the keyword independent for question 1, 2, and 3. Because it has that specific assumption. That's why we can just using the summation there. Any question or comments? Okay. Question 4. So I think that question is asking about playing some game and then probability of losing more than $75. So yeah, so I use X to denote the gain of each game. So this will be similar to coin toss. So we have our support is +5 and -5. You either win $5 or lose $5. So the support is, so X can be equal to +5 or -5. And then I think, yeah, there's also 2 keywords. One is independent, one is fair, the fair game. So that means the probability for each event is also 0.5. So now we calculate the expectation of random variable X. And here we use summation X multiplied by P of X, the definition of expectation. And we plug in the number. So 5, we have a 0.5 probability winning, gain $5. So 5 multiplied by 0.5, and another 0.5 probability of losing $5. So the expectation is just 0 for one game. And then the variance of X, it just, we also use the second moment minus the square of the first moment. So summation X squared multiplied by P of X. So 5 raised to the power of 2 multiplied by 0.5, and then -5 raised to the power of 2 and multiplied by 0.5. So the variance of each game is 25. We still have -0 squared, but yeah, it's just 25. So yeah, mean and the expectation and the variance. And now we are interested in this quantity S here, which is the sum of 50 game. So we also consider 50 as a relatively large number, and then the S approximately follow a normal distribution. And then mu of S is equal to n multiplied by mu of X. And the variance of S is also n multiplied by variance of X. So we can just plug in a number for n equal to 50, and then expectation 0 and variance 25. So then S follow a normal 0 and 1250 as variance. And then this is the quantity we are interested. So losing more than $75. So we convert S from a general normal distribution to a standard normal distribution by minus the mean and over the standard deviation. And yeah, so under the standard normal distribution, we are interested in Z less than equal to 0.212. And then you can, using a Z table or function to calculate that. Any question or comments? Okay, then for question 5, so we have, I think this question is regarding three electronic device, and then each of them follow a exponential distribution. We are interested in the lifetime of that device, so that means all 3 components fell, and then that should be considered as the lifetime for that component or for that device. So again, we're still interested in the sum of the three components there because their lifetime follow exponential distribution. So we're interested in the sum of the lifetime of that device. I think that's the setup for the question. And then, yeah, so here we are, again, we are interested in the distribution for S. And in order to get that, we can use the moment generating function here. So we're talking about the moment generating function with respect to the random variable S. And S can be decomposed to the product of the moment generating function of the individual component, or in this case, it's just x1, x2, and x3, where each of them follow a exponential distribution. And because there's a keyword independent, that's why we can decompose S into a product of the three individual moment generating functions. So once we have that formulated, and then we can now solve for the individual component. Since each of them follow an exponential distribution, we can just do one variable x, and then take the product. So this is similar to what we did last week, or exactly the same for moment generating function of an exponential distribution. So this is expectation E of tx, and that is the definition for the moment generating function. And now we take the integral for x ring. Question?
Wondering, did we just plug in the formula without having to derive it, or would we lose points?
I'm not sure how the grader will grade the homework, but if you just directly apply, so you were saying you just directly use the moment generating function, right? Without, as long as you specify or just write that this is the moment generating function for exponential distribution, just maybe add a sentence to point it out that you just directly use it. I think that should, but it depends on the grader. Any other question or comments? Yeah, so instead of so for on this slides, I was just more of a recalculate from scratch. So yeah, so take the integral and E of tx multiplied by f of x, and this part is the PDF of the exponential distribution, and then lambda outside, and then that's a constant, and then we're trying to evaluate this integral. We let u equal to that, and then x is just equal to 1 over lambda minus t multiplied by u, and then dx is just this multiplied by du. And we rewrite this integral here as exponential of negative u multiplied by a constant du. We rewrite this integral from with respect to x to with respect to u. And then we can now evaluate this integral. We will get, and at that bound, and then we have 1 over lambda minus t. And we still have a constant term lambda here. So finally, the moment generating function for an exponential distribution will be lambda over lambda minus t. So if you directly apply or just using this, so your answer probably start from here. You can just mention that, okay, this is the moment generating function of the exponential distribution. And then, we also know that the average for each component is 100. And then the expectation of the exponential distribution is 1 over lambda. So we know that lambda is just 0.01. And similar for the other two, x2 and x3. And once we have the moment generating function for the for each of the xi, then we can just take the product, and then the moment generating function for s is just lambda over lambda minus t raised to the power of 3. And now, this is more of a as a given information so we also know that the moment generating function for a gamma distribution will also have the form like this. So lambda over lambda minus t raised to the power of alpha. So we recognize that, yeah.
Well, I was just wondering, so like for these type of problems, is it always the appropriate steps just taking the moment generating function and then trying to match it to a distribution using?
Yes, because moment generating function is more of like an identity. So if you see it looks like this, then you can tell right away this is a gamma distribution. So yeah, you can use it as a key or as an identity.
Okay.
So when you see this, yeah, because all the gamma distribution will have the form like that. Yeah, it's just different alpha and different lambda. Yeah, but if you can reduce to that form, then yeah. So we reduce to that, and then we now basically just can recognize our original, or the distribution for random variable S is actually a gamma distribution with alpha 3 and lambda 0.01. So what we did here is that the individual component follow an exponential distribution, but the sum of them actually follow a gamma distribution. And yeah, and also we know what the parameter are when we just matching the two distributions. Yeah.
Yeah, I just think it like feels kind of weird how we need to like prove the exponential one when we're expected to match with some other one. So like that's kind of assuming that we know the moment generating functions of all the other ones anyway. So.
Yeah. Mm-hmm. Yeah. Any question or comments? Okay, then for question 6. So we have two bias coin, and then from a drawer. So we have probability 0.5 selecting coin A and 0.5 selecting coin B. Then tossing a coin, the probability of getting a head, it will be 0.5 multiplied by the probability of coin A landing on head, and 0.5 multiplied by the probability of coin B landing on head. So that will be the probability of getting a head from a random from one toss. Yeah, let x be the total number of heads obtained in n trials, and then x follow a binomial distribution. Yeah, because we also have two discrete value for in the support. So yeah, so this is the binomial distribution, where the p here is regarding to this p for randomly choosing one of the two coins and then getting a head. And yeah, so when n is large, x can follow a normal distribution, where the mean is just the mean of the binomial distribution, so which is n multiplied by p. And the variance is just the variance from the binomial distribution, and np multiplied by 1 minus p. So if you also take minus the mean and over the standard deviation, you will get the standard normal. Yeah, so here it's all talking about when n is large, and then we can approximately consider that as a normal distribution. Yeah.
We can have cases where we get the norm like and it's not 0 and 1, right? Or
So
or we can get like the normal distribution and it's not 0 and 1 given for 6, like where it's just mu and sigma.
sorry, I don't. What do you mean?
So So you'd have like mu is equal to NP,
Uh-huh.
and then sigma is NPQ,
Yeah.
and then that wouldn't be like a normal 0 form, or I guess, right?
Sorry, I still don't. If you minus the mean and over the standard deviation, it becomes standard normal. Is that what you're?
Oh, so that'd be just Z then.
Yeah, this is a general normal. If you do the minus mean over standard deviation, it reduces to Z.
Okay.
So this is Z follow a standard normal, and this is talking about X. But these two are basically the same thing, right? If you have a Z, you can get this one. If you know the NP and NPQ. Yeah, so these two are basically talking about the same.
So we have to find either one of those, or do we have to go from the
I think for here, for here is it should be fine. Yeah, but this is just more of a, if you keep reducing, it would be a Z. Yeah. But they're talking about the same thing. Yeah. Okay, then for question 7. So we also have 2 coins, and then but this time we select one and toss it twice. Or yeah, I'm not. I don't remember the question. Yeah, but yeah, for tossing a coin twice, we have to support 2 heads, and then 1 head and 1 tail, and 2 tail. So let X subscript A denote the number of head obtained in 2 tosses using coin A. Okay, so yeah, we randomly choose a coin and then using that coin tossing twice. So we don't put it back or choose, yeah. So select 1 coin and toss twice, and the probability of getting 2 heads will be X subscript A equal to 2. That means we have 2 heads. So that's the first case. And when XA equal to 2, it will be P1 squared. So the probability of getting 2 heads. And then for X subscript A equal to 1, that means we have 1 head. That is the middle 2 cases. So we have 1 head, so P1 multiplied by 1 minus P1. And we have 2 occurrence, so we multiply by 2. And the last one, when XA equal to 0, that means we don't observe heads, so 2 tails, so 1 minus P1 squared. And similar for coin B. So yeah, so this is randomly select a coin for 1 time toss twice. And I think we are interested in doing that n over 2 times. So for now, we denote X, so without the subscript, so X as the number of heads obtained in 2 tosses. So that should include the cases where we randomly select coin A or coin B. So the expectation of X is now 0.5 multiplied by the expectation of XA, and 0.5 multiplied by the expectation of XB. And then we reduce to P1 plus P2. That's the expectation of X. And then we have the variance of X, where we first need to calculate the second moment. So 0.5 multiplied by the E of XA squared plus 0.5 multiplied by E of XB squared. And then it will reduce to this expression here. And we also need to minus the EX squared. And then we will have this expectation and the variance for the random variable X, where we include both the randomness for choosing both either coin. And once we have the expectation and the variance, we can now talk about for n over 2 times, which we denote that as y. So y is the number or the total number of heads obtained out of n tosses. So then the expectation of y just sum over of n over 2 occurrence. So it just n over 2 multiplied by p1 plus p2. And then the variance is also n over 2 multiplied by the variance of this. Yeah, and then when n is large, y will follow a normal distribution. And if you use y minus the expectation of y and the standard deviation of y, it will just reduce to a normal, a standard normal. Yeah, so similar to the previous question, except that the expectation and the variance are slightly different.
For that problem, instead of standardizing it, can we also write as like Gauss normal distribution with the
Yeah. If yeah, so you are talking about like that, right? Yeah. Basically these two lines are the same. Yeah. Yeah.
Is that p1 plus p2 over 2? Or I guess since there's two trials, we multiply it by 2?
Sorry, which one?
Or, yeah.
So expected value is EY equals n over 2 times p1 plus p2, but can I just denoted p1 plus p2 equals as p, but for me, for p is p1 plus p2 over 2, but is it, should we get rid of 2 because it's 2 trials?
Sorry, what should be the expectation?
For me, I got the expectation of n over 2 times p1 plus p2 over 2, but I'm not sure why why are we getting rid of 2 over 2?
Oh, so you were saying there should be another over 2,
Yeah,
right?
that's what I did, but maybe I'm wrong.
Yeah, maybe this solution may not be correct. If but so this is the expectation for doing one time, randomly choosing a coin and then toss it twice, right? But we have n over 2 occurrence, so we just added. So you were saying this should be n over 2 and then p1 plus p2 over 2, right?
Yeah, that's
So
what I did, but
where I'm not sure. So where is the second or the 2 in the denominator come from, or from?
I guess it's from like one coin toss from the previous problem. Like from number 6.
Mm-hmm.
Number 6 was for one coin toss.
Mm-hmm.
I guess I cleared that over.
maybe like they divide by 2 because tossing it twice. So like
But
they
this.
divided like probability of each individual one we like divide by 2.
Yeah, but
I think the solution is like
yeah, because this expectation or this p1 plus p2 already included the 2 tosses for one. So yeah, so this is the for 2 tosses. Yeah, and then you have n over 2 occurrence, so you just n over 2 multiply by the expectation. Is that what you're? Yeah. Because the expectation already included 2, and you just observe, and then you just do that n over 2 times. So n over 2 multiplied by p1 plus p2.
Are these going to be posted on Canvas?
This is currently recording, so it will be a video. But I probably will not post the slides as this is the solution for your homework. So, yeah. Any question or comments? Okay, then for question 8, direct application of a moment-generating function. So E of Tx multiplied by the PDF, where the PDF is the uniform distribution, or more explicitly 1/2. And yeah, basically just solving this integral. And then you will find the expression for the uniform distribution ranging from 5 to 7. Yeah.
That's supposed to be discrete case or continuous case?
It's uniform distribution, right? So it should be continuous.
But there are also like discrete uniform distributions, right?
I'm not sure. I thought uniform distribution is only continuous. I don't know if there's a discrete case for that.
Okay, because yeah, when I Googled it, they had like discrete cases, so
Oh.
that's why I was confused.
Okay.
I did both cases, but
Oh.
it's completely
I don't know about the discrete case, but yeah, here, but in this slice here is talking about the continuous case. Yeah. So I just used the integral and then ETX multiplied by PDF.
Yeah.
Yeah.
For that one, I kind of made a piecewise function because like t can be 0, right? So like I kind of said like when t is not equals to 0, it's that function, but when t equals 0, I say it's like a 1.
Oh.
Is that necessary? Because like if you have a t equals 0, you do like something divided by 0 for moment generating function.
That's a good question.
So it's undefined when t equals 0. That's like what like when I looked up like online, sometimes it has like a piecewise function where it gives different moment generating function.
I didn't think about that, but yeah, but I think if you leave it as this form, it should be fine. Yeah, but I didn't think about if there's a when t equal to 0, and yeah, t can basically ranging from different value. Yeah, but yeah, I think leave it in this form should be yeah. Okay, then for question 9, we have random variable z equal to 2x plus 4y. And yeah, so here we're talking about the moment generating function, and we decompose the the moment generating function for z into the product of moment generating function for x and the moment generating function for y. And each of them follow a gamma distribution. So now we just work on the individual moment generating function. So this is the moment generating function for a gamma distribution. So definition, E of t 2tx multiplied by the PDF. And this part is a constant, so move it outside to the integral. And then x alpha minus 1, and then E of lambda minus 2t, and then x. And now we can, this might be difficult to evaluate, so we are going to substitute some of the variables here. So we let u equal to lambda minus 2tx, and then x is just 1 over lambda minus 2tu, and du is that constant multiplied by du. And then back to the integral here. So we now talking about this integral here. Later we'll multiply back the constant term. And so x alpha minus 1, it's just this part, and then raised to the power of alpha minus 1. And this part is just e to the power of negative u. And then dx is just this part multiplied by du. And we also change the domain or the support from x to u, and it also under this range. And here I move the u raised to the power of alpha minus 1 outside the parenthesis, so additional u alpha minus 1. And then this 1 over lambda minus 2t will cancel out with this minus 1. So we are only left with this raised to the power of alpha. And we can move it outside the integral, and this will be a constant term. And then this part, it is more of a property. This part will reduce to a gamma function. So this entire integral here will reduce to gamma of alpha. And this will cancel out with the denominator, and then this will be the gamma distribution. Yeah, so yeah, without working from scratch, if you want, or you can just directly call this, or just specify that, okay, this is the homogeneous function of gamma, and I'm going to use this as, yeah.
So when you have m to the 2t and m to the 4t, like, does that constant go into play, like, with the, just calling the function, like, does it affect it?
If I understand your question correctly, I think so you have there are two concerns on this part, whether the 2 should be considered as for 2t or should be considered as the variable or homogeneous function for 2x. So that could be confusing, right? If that's your that could be a concern. So if that's what your yeah, but for this part, I will just put the t in put the 2 into the t. So I'll just consider that 2t is my new t. And then I apply the same. Is that your concern? Yeah, because that, yeah.
Okay, so wherever t would be, you just put like 4t or 2t.
Yeah, so here I consider 2t as my t.
Oh.
So that's what, yeah. But yeah, that could be a problem if you're working on, or if you're using that. Yeah. But yeah, here I'm just, yeah. That could be a concern in the future if without careful to the detail. Yeah. Yeah, but for now we just reduce to that, which is the homogeneous function for gamma distribution. Or yeah. So here we have 2t here. So yeah, so what I was doing is that I considered this 2t as my t. But yeah, because the question didn't ask for any further development, so the concern does not shows up. But yeah, if it asks following question, then this 2t might be yeah. So yeah, so regarding for this 2tx and 4ty, basically their their homogeneous function will be reduced to 1 over 1 minus t raised to the power 2. Back to the homogeneous function for random variable z, we have 1 over 1 minus t raised to the power 4. Again, we recognize that as a gamma distribution for alpha 4 and lambda 1. Yeah, so the product of, or the sum of a gamma is also a gamma distribution. Yeah, so I think previous question is sum of exponential is a gamma. So this part is sum of gamma is also a gamma. It's about time, so I'll just briefly go over this part. So for part A, you just take the derivative with respect to t and then set it equal to 0. First moment, second moment, you should be able to find the variance. For part B, for the first one, if you take t equal to 0, it's 0.5, which or violates the definition. When a homogeneous function when t equal to 0 should be equal to 1. So the first one cannot be a homogeneous function. The second one is that if you take the first and second order derivative, find the variance, it actually gives you a negative value, which cannot be true for a variance. So the second one cannot be a valid probability distribution, or it is not a homogeneous function. Yeah, so the first one and the second one has a problem that violates some other definition. Yeah. Okay, that should conclude homework 1.
Which means that third one is solid.
Okay, I will pause the recording here.